What's the the other one and now you come at it. People come at draw a bunch of lines and make them all.
Yeah.
OPU has that.
So, yeah, there's
Well, that made your system. That's what I do. It takes the electrical, mechanical, software. Oh, here, oh, yeah. Thank you, Jim. Okay. Have you talked to my? Remember you had stuff on the table. Yes. Oh, yeah. Those are all what you did? Service or product? Service or product? Come up with something. Something that you look at it a lot. Try. My TS is to enjoy things. Then I was what did I see over there? Wow. We had that. A lot of stuff. Yeah, whatever. Most interesting thing I found on the AI, there's a big display. There's somebody probably talking in, and you're talking about this, so you couldn't tell. Yeah, created. We can buy them all. If you have a laser, Oh, we could put a microphone next to no, he doesn't.
It's 7 o'clock. I'd encourage folks to wrap up dinner, grab additional sandwiches and cookies for the talk, and bring a chair over and start talking.
I want to go now. They're doing it there. My friend got the I thought, I said, well, that's not right. Take it there and fight. They're eating about it. You got to drill one thing. Yeah, because it's not. No. No, I thought the water was hot. All right, folks. Thanks for coming to November's talk. We're really excited to have Carson Roberts of Headwall Photonics. Headwall's been a phenomenal sponsor and corporate member of NES-Optica for several years. So we really appreciate their support. Just a couple of announcements before we begin. On December 12th, we'll have our next talk co-sponsored with IEEE. And it'll be Professor Tammy Wang of Boston University.
on analog neural networks based on photonics and other controllable physical systems. That one's going to be really interesting. It's going to be thinking and computing with biosensing. I don't know what to expect. I'm saying. What's that? Great question. It will be located at. Where will it be? Okay, it will be here. It will be here because it will be co-sponsored by IEEE, and they all sponsor here. There's someone at the door. Okay, cool, fantastic. So that will be December 12th. December 14th, we have an outreach event at New York High School where we'll be giving off, we'll be showing optics demos to middle schoolers, high schoolers, and even younger kids. It's always fun. We'll have something up on the website to sign up to volunteer soon. It's Saturday morning. It's great fun, totally rewarding. And then I think that's all we have. The other announcement is if you ate dinner and haven't paid yet, please see my colleague Caitlin at the door to hand over your money. Beyond that, without further ado, Carson Roberts from Headwell Photonics. Thank you very much.
Thank you. Thrilled to be here. I've been to a lot of Optica meetings over time, and it's nice to be able to share a little bit of what we do at Headwell. And as you'll see, I'll talk a little bit about what some other people are doing. Just to begin with, I don't actually know anything about optics, and so I'll say a bunch of things that may seem kind of dumb. Bottom line is I can get it all to work, and so I don't really need to know anything about optics. Okay, but some of this stuff is really cool. The basic thing is we put little optical systems onto drones and fly them around, and there's some amazing stuff that you can do with them. So, okay, first technical difficulty. The arrow, maybe a down arrow. Maybe a right arrow. Maybe if I click.
Move the mouse to the other screen.
Move the mouse to the other screen. To this screen? To screen 2.
Yeah,
click on it.
Right. Now when you, yes.
Okay, there we go.
Arrows are good.
All right, thank
Okay,
you.
cool.
Thank you for the technical help here. Yeah, so I don't usually do these outlines, but yeah, what is hyperspectral imaging? I'll try and give you a little bit. There's a lot of people in this room who can give you a better explanation than I can. I wanted to talk a little bit about, I'm talking a lot about the push broom hyperspectral imagers that we at Headwell and several other people in the space make. But there's a bunch of other different ways to do it, and some of my friends in the industry have shared with me some explanations about their technology. Then I'll go a bit more into detail about what we do at Headwell, because that's the data that I'm going to be presenting. Just a little bit about LiDAR, really cool stuff. Again, I kind of know how it works, but it can do some amazing things. And then a couple of examples, one where we're going to be looking with the shortwave infrared at the mineralogy of some mine waste at an old mine out in Nevada. And the second one, using the visible and near infrared, we're going to be looking at coral. And we did some work with some folks who are trying to come up with some way of restoring coral reefs by growing different species and outplanting them. And then the last thing is what I've started to work on quite a bit recently is because we're flying around, taking data, and in order to make sense of it, we have to geolocate it. There's this whole branch of science and engineering, which is geographical information systems. And so I can take all this, I can take my LiDAR data and my digital surface models and photogrammetry and the hyperspectral data and build up these cool GIS layers. And so I'll talk a little bit about how we can use that to solve some of the problems. So let's get going. Everybody's basically familiar with this. You have a camera that takes 3 pictures. They take them all simultaneously. On your typical camera, you've got this little bare filter with 2 greens and a red and a blue. And then you generate 3 images, a red image, a green image, and a blue image, and we build it up. And what you can sort of see here is particularly the red guy, he looks very white, right? The red, let's see, this is sort of the compelling thing. In the black and white image of the red parrot looks white. And in that same black and white image, the wings of the blue parrot look black. So that's 3-color imaging, hyperspectral imaging. Let's not do 3 colors. Let's do 300 colors. And so instead of just those 3 images, we build this thing called a hyperspectral data cube. And I'll show you a nice illustration I got from my friends at Bodkin about how all this works. But this is the basic data structure where you can think of it as I have a stack of n different black and white pictures. Or if I take each pixel and look through the stack, if it's bright at this color and dim at this color, then I get a full spectrum out of it. And so you end up, it's also called spectral imaging. And so you get an image where every pixel has a spectrum. And then there's this whole science of spectroscopy that you can apply to the images and do some pretty cool stuff. Okay, so I'll talk a little bit about snapshot imagers, which is not what I use. The cool thing about a snapshot imager is you take one image and you get that whole hyperspectral data cube. And so if you can take those images at high speed, you can make hyperspectral video. Okay, and there's a particular technology that I used to work at Bodkin Design and Engineering, and their particular technology for doing hyperspectral imaging. There's another company that makes hyperspectral imagers that are snapshot. They use a slightly different technology. Another company that I've done a little bit of, looked at them, haven't really worked with them. Imaging Fabry-Perot interferometers, but it works. And then we'll talk quite a bit more about the push broom technique and how it relates to the way that we take our data. So this is, again, a picture of the hyperspectral data cube. And so you can see there's some sort of image. And then if we take a vertical slice out of it, that's a monochromatic picture. If we take a horizontal slice through it or a horizontal line through it, then each of those little lines, it was one for each pixel in the image and extends through the data cube. And each of those little lines is a spectrum. And so we get a spectrum. And what these folks at Bodkin do is reformat that all so that it goes onto a focal plane array. And then each one of them little lines becomes a pixel in the final image. But each of those pixels has that full spectrum. So you get that hyperspectral image. And the Bodkin system, it basically, the light is dispersed by prisms. You make an image onto, and most of these systems are going to have a primary and a secondary focal plane. The primary focal plane in this particular incarnation has a bunch of small holes in it. Each of those holes is re-imaged onto the secondary focal plane where there's a detector, and that becomes a streak, and there's your spectrum. And here's an actual example from some data taken by one of these BDE imagers. And you can see the spectrum. This is mid-wave infrared, and they're right around 4.5 microns. I can't remember the exact number. You can see this little dip because there's always a bit of I'm sorry. Now we should. Right. So the basic idea is you have full plane array photo detector, but you can also say, I don't want the whole thing. I just want one strip. Why would you do that? Because you can then take that one strip of pixels and disperse each one of them, and you get a bunch of rainbows. And so if you remember from that snapshot image here, where it's a bunch of little lines all jumbled around on the plane, they're all parallel to each other. And so then each picture that we take is just one line of data, but it gives us the full spectrum. And here's basically how it works. It's called an Offner relay. I like to think of it as a 3-mirror array. That's how you can make a 1-to-1 imager. And so we've got we have a 4-optic. The 4-optic makes an image onto a focal plane array, but the focal plane array is all opaque except for this one line that's about a pixel or two high. That is then re-imaged through a concave mirror. Oh, mouse. Any idea where it is? Yeah. Through a concave mirror onto a convex mirror, which happens to be a diffraction grating, then onto another concave mirror, and then it's spread out onto the focal plane array. And so again, take one image and you get some number of pixels, let's say 1,000 pixels, and then each of those is dispersed into 300 or 400 different colors. And then again, you get this spectrum from each pixel. But we're going to be flying these things around in the air. And the platforms aren't going to be stable. So it's going to be looking this way and looking this way and looking this way. And then how big do we make the pixels? Well, and this is this weird thing about optics. Really what's happening is light's coming from the world and it's being drawn through the optics and projected onto the pixel detectors. But another way of thinking of it is that each of those detector pixels is actually, if you think of it as making light, then it projects back out the other way, and it's going to make a spot that's going to depend on the focal length of the optics and how far away things are. And so that's what we do in order to make reasonable images out of these wobbly things that we get from the drones, is we need to project it down onto the ground. We need to know where the ground is, and we need to get rid of some of these perspective distortions that we get. So complicated algorithms that work mostly. You take the raw image. The raw image, every one of these lines is exactly this. An older imager of ours, 640 pixels across, 2,000 pixels long. And you can see in this one right here, the drone pitched forward. And if we go, right here, you can say I've got this square top, the edges are wobbly, and that's because the drone was rolling. And then when we apply, when we reproject this thing down onto this digital surface model, we now get an image where the edges are wiggly, but the interior is square. That's a properly orthorectified image. And that wobbliness on the edge of the image is essentially the time history. Yes, it's pretty complicated. And as my colleague here, Charlie, can tell you, it's a pain in the butt to actually get it all to work, but it does. Okay? So next thing, LiDAR, light detection and ranging. The systems that we use, we've got 16 paired photodetectors and lasers. Laser fires a pulse, and then the photodetector waits and measures how long till that pulse comes back. Divide that by the speed of light, and you get the distance. And so you get a whole set of numbers of what was the angle, what was the distance, and then if we use an accurate GPS inside the data acquisition system, we can know exactly where the LiDAR was, and then it tells us, okay, there was a point that was this many meters away at this angle, and then there was one there, and we can use that to build up and now I really apologize. I don't know why this is screwing up. I've lost my projection. Yeah, well, it came from Microsoft. I can't get the mouse to, I want to just go to project.
It seems like the screen itself.
Oh, okay, we can see it there. There we go. There we go. Bring this over here. No. It's what, 270? Yeah, yeah. Yeah, okay, okay. Yeah, there are a couple people climbing on it. One of them's me, and the other one is my colleague Charlie. We go down here.
I don't know why this is very strange.
So we've lost, there we go.
No, okay,
Now
okay.
now we get the
Yeah, yeah.
project.
Okay, here we go.
Okay,
Ah, all right.
and now we need to move back to that one and click on that screen.
Yeah, 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 yeah.
Okay. And then, okay, and this is, we take all those points and integrate them with the GPS, and you can see that's a half a second. There's 8 colors repeated twice. That's the 16 lasers. We're traveling forward and we're slowly building up this point cloud. And one of the things I want you to notice is the LiDAR, it gives 360 degrees of view. It's designed to be mounted horizontally looking forward, but we mount it vertically, so it's sweeping along the ground. That means that part of the time it's pointing up, and we'll get reflections from the rotors on the drone, so that becomes part of the point cloud, which is a problem, but also an advantage, because then we can actually see the trajectory of our thing in the point cloud. Okay, so now I want to talk, and I'll show you some more about the LiDAR stuff in a minute. Now I want to talk about when you actually want to go out and do this. It's not easy, and there's a lot to it. How do you get some high-tech system out into the middle of nowhere or out into the ocean and reliably collect data? So this was, we're out in Nevada looking at some geology. We got 2 trucks, got to bring lots of drinks. You got to bring a generator, a table to set up on. You never can have too many people in one of these field missions. You can see our drone sitting on the ground there. And I think in that picture, I'm driving the little drone that's actually taking the picture here. There is one of our sensors. That white one actually has inside of it a visible near-infrared sensor that sees from 400 to 1,000 nanometers, and a short-wave infrared sensor that sees from 900 to 2,500 nanometers, and it's got a LiDAR on it. Flies on this DJI M600 drone, and it'll fly for about 15 minutes. We can also put it onto a rotary stage. Remember, it's a slit scan imager, and so as it rotates, you can look at different things and you can build up the image that way, as long as you're scanning the slit vertically across your scene. You get nice images from rotary scans, but you don't get the GPS, so you can't geolocate anything. All right, so what do? We collect the data, we collect the LiDAR data, we make a LiDAR point cloud, and then we use that to make a digital elevation or digital surface model. Remember, we need something to project all the data onto in order to know how big the pixels are and what their latitude, longitude coordinates are. And then we use some calibration. This is going to be true for any hyperspectral imager. Use some calibration, because what you get off of the imager is digital numbers, some number between 0 and 65,000. Then that needs to be converted to something like a flick, which is a watt per square centimeter per steradian per micron. Then we convert those reflectance, those radiance data to reflectance. That's the chemistry, right? Because the reason that different things have different spectra is because their atoms and electrons are absorbing or not absorbing different wavelengths of light depending upon their particular energy resonances. So you convert it all to reflectance, and then we can then do spectroscopy on it on an individual pixel basis and say, this pixel is a tree, this pixel is water, this pixel is a rock, this pixel is, whatever. And then we can take those classified images, we can ortho-rectify them, and we end up with these nice classification maps where you can look on the ground and say, this stuff is here, and this stuff is here, and this stuff is here. So this is a sort of an example from the shortwave infrared again, okay, where we start with our raw data, and it's kind of noisy, and there's a bunch of these dips. Those are atmospheric absorption bands. It's solar dark there. So when we're flying outside, we don't get data there. This particular one is really frustrating down here around 1850, because that's an OH absorption band, and a lot of the minerals that we're interested in The difference between them is their hydration state and how much OH they have, but we can't see that because there's no light, because the OH in the atmosphere is already absorbed it all. And then we convert that to radiance, and then we can convert it to reflectance. And again, those atmospheric absorption bands, they just go nuts. You're dividing 0 by 0, and so you don't get good data there, and you want to mask that out. And I'll show you how we do that in our analysis. Again, what I showed you before, you take this data that starts out looking pretty bad. And I don't know if you noticed that we don't have this sensor on a gimbal. So it's really just flopping around as the drone goes around, but it's got a really good GPS and inertial measurement unit. And so we always know where it's pointing to a fairly high degree of accuracy. The one that we use gives us a stated accuracy of about plus or minus 3 centimeters horizontally, about plus or minus 7 centimeters vertically. And typically when we fly these things, again, depending on the altitude, we're looking at 2 to 10 centimeters size per pixel. And so it matches pretty well with that sort of a GPS IMU. So an example, right? This is going to be shortwave infrared because I'm interested in mineralogy. And so this is a place out in Nevada. There was a mine there in the 1860s or so, and they left a big pile of waste. They left a big pile of waste there. In the 1860s, nobody cares. A lot of these ores are sulfates. You put a big pile of sulfate rocks out on the ground, it rains, they drain sulfuric acid, it poisons the creeks, kills the fish and stuff like that. And somebody had the brilliant idea sometime in the 70s, oh, we'll cap it all up with a bunch of clay. They did, and it went through, and there's still a bunch of stuff. And so the idea was, can we see any of these minerals by looking at this hill spectroscopically? Well, we're using the LiDAR. And the way they did it was they had a mine at the top of this hillside, and they drilled a shaft down, and then there was a drift that went out the side, and that's where they took out all the stuff and left the waste. We flew the whole hill in order to get a digital surface model that we could fly over. And when I'm looking, and then because we have this geolocated imaging data, we can fuse that with the point cloud to get this three-dimensional image. And when I was working on it, I said, what the heck is going on? There's this stuff underground. I've got some errors in my LiDAR point cloud. No, actually, that's the mine shaft. And by looking and doing some measurements, we were actually able to see about 15 meters down into the ground from the top of the hill. Pretty cool. And the other thing that you should notice from this is false color RGB from the shortwave infrared, but those funny looking piles there, that's also mine waste. That is the spectrally active clays that are associated with the ores. So we did that first flight, and that allowed us to generate a very accurate digital surface model. We can load that into our flight planning software and then fly at a constant altitude above ground level. That's important because that means the magnification is constant. And so we can stitch all our images together, and our pixels are always going to be about the same size. And again, remember I said you get a little bit of reflection from the rotors of the drone? Well, that's where you see the trajectory here. And we were flying up and down the hill and up and down the hill. And that's how we built the images. I already showed you the RGB image. And then I'll show you a little more about the SWIR. From another project that we did a while ago, we had a spectral library of a lot of the minerals that are associated with these porphyry copper deposits. And so notice a bunch of different spectra, got some ups and downs. See how I've got some areas blocked out? Those are those atmospheric absorption bands. I'm not going to get any good data there. I'm not going to do any comparison of my spectra in those regions. So I've got all these, not from the same place, but it's going to give us an idea of what sort of stuff that we have. And so here is the RGB orthomosaic. And then next to it, I've classified each pixel in the image according to which of those spectra in the library it most looked like. And here's the key to what the different ones are. I don't pretend to know what any of these minerals are, but the people who looked at it was like, yeah, there's got to be a bunch of jarosite there. And the other thing is that clay cap obviously didn't work because this stuff doesn't look like the stuff all around it. And again, you know, we do have the ability to fuse together this LiDAR and hyperspectral data to make these really cool images. Still not clear to me what their actual value is, but everybody who looks at them thinks they're pretty cool. I think they're pretty cool too. And so that's sort of the bottom line of that is, yes, we can see this mine waste. And if we go with a bunch of geologists and collect a whole bunch of samples, take them back to the lab, measure them with some lab spectrometer, we can rebuild that spectral library and do a more accurate classification of all those different pixels. So, cool thing, shortwave infrared with LiDAR, we're doing some geology. Let's shift gears a little bit and think about coral reef restoration. So you all know that as the climate gets warmer and we get more CO2 and more ocean acidification, corals dying all over the place. But the idea is, well, maybe there's some species, maybe there's some breeds within species that are more robust. And so there's people who are actively going out, collecting pieces of coral, growing them, and then choosing the ones that they think are the best, and then taking those back out and literally gluing them down onto the reef and hoping that they'll grow. And so they have a bunch of tanks. We were working with this Moat Marine Lab down in Key West. And first we took our imager, this is going to be the visible near infrared imager, set it up on this rotary scanning stage to look down into the tanks. And so each time we take a picture, we'd set up, you can see in the corner here, let's see, yeah, this right here is a calibrated part. So that's got some special paint on it. I know exactly what its spectrum is. I have that saved digitally, and I can take that radiance image and then look at the radiant spectra from that tarp, and I can then convert everything into reflectance. And this particular imager, we did 2 radiometric calibrations, one with this 23 millimeter lens where I could adjust the focus, and another with a 12 millimeter lens where the focus is glued down. That's set to infinity, and so as long as I'm beyond the hyperfocal distance, which we always are when we're flying, we never fly below 30 meters above ground level, then everything's going to be in focus. The actual process of focusing one of these push broom imagers is hard because all you see is a bunch of streaks. And basically what you want to look for is 2 objects in your field of view that are small, and one's bright and one's dark, and you want to get those streaks to be as narrow as possible. That means you're focused as best as possible. But as I showed you from that that snapshot imager, you can get a lot of information out of an image that's not in great focus. So what do we get? This sort of struck me as, wow, these polyps over here, they look kind of like sea anemones, but they seem to be pretty bright green in the middle. And when I look at their spectra, I see this really sharp peak right here. And this corals are closely related to jellyfish, and people who work in biology, everybody knows about the green fluorescent protein that originally came from a jellyfish. This is that same protein. And so these guys are actually fluorescing. So that bodes well for us being able to see them in the ocean. And in doing this, I actually found 2 different types of fluorescence in the various corals that I looked at. And I used a thing that's not really a hyperspectral thing, it's more a multispectral thing. It's called a normalized difference index. And that's where in spectroscopy, you take 2 different wavelengths and you take a normalized ratio, A minus B over A plus B. And that gives you some idea of how high this difference is. And so in this case, I want to see how strong is that peak at 512 nanometers. I found another one where there was a peak at about 488 nanometers, blue. And so I was able to come up with 2 indices that I could use to apply to this hyperspectral data and maybe more easily have those particular fluorescent species pop out. So I make another RGB image. Now this time the red is red, right? That's 670 nanometers. The green is my green hyperspectral index, and the blue is my blue hyperspectral index. And what you can see is on the left-hand side, you can see these polyps with the green spots, and in the green hyperspectral index, they're white. And then if we look over here, there's one species of coral which really looks kind of blue. And if we go down, they are quite a bit brighter here in this blue. Again, monochromatic image. which is derived from the hyperspectral by a normalized ratio of bands. And so those were the little plugs, and each one of those, they're about an inch across. And they take a very small, like about a centimeter piece of coral, they glue it down onto this little piece of ceramic, they incubate it for a few months until it has grown out to cover it, and then they put that back out into the world. And then here is the recently harvested coral that they're about to cut up. And if we look at those, we've got some green and some blue, and not surprisingly, you get a lot more fluorescence where there's sunlight, because we're operating under a canopy, and you can see a shadowed area right here where I don't see much fluorescence. I certainly don't see it here, and so cool. Now we've built up something that we think we should be able to use to identify coral, and so let's go out and actually take some data. Okay? Well, this is a good couple miles offshore off Key West, and there's the deck of the boat, and there's the drone, and there's Charlie and me. This drone, it's this big, and it's got 4 spinning blades of death, and we've got about 1.5 meters by 4 meters to take that thing off and land it. Doesn't sound very reasonable. We have to set up the acquisition with a computer. You can see an Ethernet cable going into the system. This particular one, DJI M300 drone, and it's got our visible near infrared imager, again, 400 to 1,000 nanometers, and then it's got this 16-channel LiDAR, and it's got this accurate GPS inside it. So taking off, we decided that's going to be pretty easy, right? Everybody go to the back of the boat. Charlie stands towards the front, takes off, gets up to the altitude, and we'll pan back a little bit. And you can sort of see everybody. And so not too worried about that. But then we got to bring the thing back. And so Charlie and I spent some time out the back of our shop. I said, I don't know how big the boat is, but I think the deck's about the size of this little patio we have. So I'll stand here and I'll land the drone. I know how to do this. So I stand there and I land the drone. And at some point, it's coming at me. It's about 4 feet away at neck level with these spinning blades of death. I did it. And I said, I don't think that's a very good idea. Charlie says, let me try. He says, I don't think that's a very good idea. So what are we going to do? We've got to get this thing back. What's the safest way to do it? And this is, what's the safest way to do it if you have not that bright people? So you take the dumb guy, give him a helmet, give him some gloves, and he stands on the pitching boat while the smart guy is way back driving the drone. And the thing is, these drones are very good, and they'll sit very still in the air if you take your hands off the controls, and then go, got it, shut down the blades, and then I hold it still. Charlie drops the controls, comes over and takes the other side, and we put it down, and we can and there I am with my knees balanced against the back of the boat, and we did this 4 times, no problems at all. We'd be happy to do it again. But again, it's kind of weird. If somebody told me, hey, what I want you to do is go out on a boat and, oh, by the way, this system, it's something like $100K. I want you to go out on a boat, get this thing that's similar to the price of your house that's going to be flying at you, and you're going to grab it out. Oh, yeah, great. That sounds like a really good idea. But it worked. Okay. And so then what we did, just like I showed you with the mine waste thing, we want to fly in a straight line at a constant speed, at a constant altitude above ground level, and then turn around and come back and turn around and come back, and we build up this mosaic that way. So all these mosaics you've seen before, they have a sort of a stripy characters that you can see on the edge, and to the extent that we've done a good job with our orthorectification, you can't really see it that much in the middle. So we got some information from the Marine Lab people. Here's where we put the coral. Charlie generates a bunch of flight plans. We go out there and we take off and we fly back and forth, and we land and we change batteries. We take off and we fly back and forth and land and change batteries. And we generate these flight lines. So you can see here, this is one of my orthorectified lines, right? because it's got the wavy edge, right? So the stuff inside should be well geolocated. And I look at it and, oh gosh, I'm not getting anything beyond 580 nanometers. Well, if I've been smart and done some research, I'd have looked up the optical transmission of seawater and said, well, that's how it works. Okay, that's not too bad, because remember those two indices, one of them's around 488, one of them's around 512. We should still be able to see those. Okay? And then I've just started working with this sort of industry standard package called ENVI. And if you look at the data on the left, it's pretty noisy. If you run it through this minimum noise transformation, it's a principal component analysis thing, kind of like using Fourier transforms to sharpen up your imagery. You take this thing, you divide it up into components, you get rid of the high frequency components, you transform back, and you get the fundamental stuff. And so you can see how the spectra go from very, very noisy to much smoother. And so that looks like it should be good for us to identify these things. Okay? And then I look here, and I've got all these flight lines, they stitch together. And this is where I've started to use this ArcGIS program to bring everything out. And a couple things, I was able to come up with spectral classes for dark rocks and seaweed on the top of the surface, solar glint. There's a lot of that. There's always going to be when you're flying around. Another thing you'll notice is this particular system, we didn't know until we were out there in the field, had a bad hard drive. So every once in a while, it would drop a few frames. So everything that we have is accurately geolocated, but we're missing a little bit of the data. Not that big of a deal, because we're still going to see a lot. The other thing that was kind of weird was the classification went to hell in the southern edge. And then I go out and look, and well, yeah, of course, we're right at the edge of the shelf. And so the water is dropped off really deep. We're at about 6 meters where we were flying, and it drops off pretty quickly. So all that seems good. But I didn't see any coral. Didn't see any coral anywhere after we did all this dangerous stuff. And after we proved that we could see coral. Why not? Maybe am I in the right place? Did my orthorectification work? Well, what I've done here is I got a few of these flight lines and I'm flashing them on and off. You can see some sort of pattern on the bottom. Looks like they kind of match. So the images that I took look like the images that I got from the National Agriculture NAIP imagery. If I look a little closer, I can actually see that our two data sets, I can see the same features, and they're offset by just about 6 meters from each other. I could fix that a little bit, but I'm not 10 miles away. So here's the deal. If you look here on the western side, Pelican Shoal 1, Pelican Shoal 2, and Pelican Shoal 3, those are the places they did the outplanting. Here's where we flew. And we had been told this is where they did the outplanting. So not blaming anybody, but it wasn't me and Charlie. And so cool thing, we had a lot of fun. Those people are actually interested now in getting one of our systems for looking at the coral in their incubation systems. My idea on this is, going forward, what I'd like to do is take that drone, take off just as we did, fly around a little bit to initialize the inertial measurement unit. You need to do that for these. You need some motion to get some acceleration, because the inertial measurement, the roll and the pitch and the yaw, these are accelerometers. So you need to give it a bunch of acceleration. Then once it's initialized, I'm going to land it, I'm going to strap it down into a glass bottom dinghy and drag that back and forth. No glint, but I'm going to be getting the accurate geolocation information from my initialized GPS. So if I can convince my management and maybe somebody else to pay for this, we'll be going back down, and this time going over the right area. And I have some reasonable idea that we'll be able to see what we need. And again, we were taking LiDAR data, but what kind of interesting stuff can I get? We're just looking at the surface of the ocean. But we did see one interesting thing. So again, I can load these, in addition to loading photogrammetry images, hyperspectral images, digital surface models, I can actually load the LiDAR point clouds directly into this ArcGIS software. And so I've done that, and we got flight 1, flight 2, flight 3, and flight 4, and I've colored these with yellow being high and green being low. Surprisingly enough, when we were out there for a couple hours, sea level was not constant. It was going down. And it went down from flight 1 to flight 4 because the tide was going out. So at least we could see that. We see something similar there, where this then is the digital surface model that we use for orthorectification. It's a little kind of cheating because really we want to orthorectify based on the bottom, but we don't have any data for the bottom. And so we just assume a constant depth. So there's more stuff to be done on that. But in the end, we can go out there, we can take these data, we can start generating this GIS stuff. And that's it. I'd like to really, he's sitting right back there with the gray hat, Charlie Kepler, amazing pilot and a wonderful person to go into the field with. Then our friend from the University of Nevada, Reno, who helped pay for that trip out to the mine in Perry Canyon. It was really great to have so much support from the people at Mote Marine Lab. And of course, there's several other people here from Headwall. It's a big operation to make these imagers. We have people that all they do is make diffraction grains. We have people that all they do is solder stuff together. And none of this is possible without a bunch of people working together to make this cool stuff. And then, of course, I also want to thank my friends in the hyperspectral imagery, Jim and Andy, who shared some of their proprietary information with us so that we can learn a little bit more about the snapshot imagers. And that's it. I had too many slides, and then I had too much caffeine. And so the hour talk is gone for 45 minutes. I don't think anybody's going to be too upset. And I'd be very happy to answer any questions you might have about this. Thank you. Yes, sir.
Yeah, I was wondering about the reason for not using gimbal stabilization and just using the GPS. Wouldn't you get, is it too heavy, or wouldn't you get improved imagery if you did stabilize?
You get improved raw imagery. There's not as long as it's not too windy, the GPS is good enough that you don't get that many ocean artifacts. The gimbals are heavy. The gimbals, the one that we can fit on, the gimbal that we can fit onto the M300 is too small to carry our imager. And we've not found one that works. So you fly around, and Dan knows this very well. We fly around and you make a sharp turn, the gimbal stops working. Or worst of all, it spins and breaks all the cables. Also, to do the GPS, so we've got a little circuit board and an antenna. And you need to know what the lever arms in X, Y, and Z are between the GPS circuit board and the antenna. Well, if it's moving on a gimbal, you actually get reduced GPS quality. So added cost, added power, they break all the time. And the GPS we have is good enough that most of the time we don't need it. We do vibration isolation, but we don't believe that a gimbal is necessary. The raw data looks a lot better with a gimbal, but the orthorectified data looks very similar. Anything else? Yes, sir.
How much time does it take to process it? Hours, days?
That's a funny question. If you know what you're looking for, right? So if you already have some classification model, you've been there before, you've done all this, you can probably take a day's data and get it down to actionable intelligence in 3 days. Okay? For most of this stuff, I spend a lot of time looking at it. We spent a little bit of time every time tweaking the bore sighting of the orthorectification to make that a little better. But the whole process, to process the GPS data, that's something like an hour. To generate the LiDAR point cloud, again, another hour or two. To process all the data to reflectance, another hour or two. To do the orthorectification, that could take, now you're looking maybe into the second day. And then the other thing about this is it's a crazy amount of data. So you take a picture with your cell phone camera, right? That's 3 images at 8 bits per pixel, generally. You take an image with one of these cameras, that's 343 images at 32 bits per pixel. Charlie and I did a mission out in Cooperite, Nevada. We were there for 3 days, and we came home with 1.25 terabytes of raw data, which goes to about 5 times that once it's processed to radiance or reflectance. And then it gets even bigger when you take these straight things and wobble them around to do the orthorectification. And so I actually, in my day-to-day work, I spend on the order of a half a day a week just moving data around. And I'm reminded of something that I saw at some years ago at a defense conference, some defense sensing conference. And one of the guys got up there and said, nobody wants to hear this, but we have to stop storing raw data. What we want is, the military people will call them target information or cues, what here would be classified images. And so the classified images I showed you, those are 3 colors per pixel. I've done a dimensionality reduction of over 100. And so we're working on trying to make that process faster and faster and faster. But there's so much data, there's a limit to how quickly it can all be done. Yes, sir.
What kind of area do you see over this? In other words, how much will you see, area will you see over
The rule of thumb that we have is that in one flight with one of these drones, you can cover up to about 40 acres. And then, of course, if you're flying lower to get higher resolution, it's less. You fly higher to get with low resolution, you get more. But it's something on that order, tens of acres per flight. And again, if for those of you who are familiar with satellite imagery, remember this is at 1 inch per pixel. And so you're really surveying a lot. And that's a tough thing. I was just talking to some people who want to survey tens of thousands of hectares in the Australian outback. That's going to take forever. And so what I said is what you want to do, you want to fly a high altitude plane at 1 meter per pixel, do your spectral map, identify interesting regions, then go in with a drone and start looking at 10 to 2 centimeters per pixel. Yes, sir.
very curious about
In what applications? Oh, yeah. So remember I showed you when we were looking at the corals, those normalized indices? So the classic one is the normalized difference vegetation index. If you look at the spectrum of any plant, it's going to be sort of flat, and then you're going to have a bump in the green, chlorophyll's green, and then chlorophyll stops absorbing around 700 nanometers. You could say because the photon at that wavelength doesn't have enough energy to make a molecule, to phosphorylate a molecule of ADP. But so the chlorophyll protein doesn't absorb past that wavelength. Plants are made out of cellulose. Cellulose is white paper. So you go from very strongly absorbing to very strongly reflecting. And if you take a ratio of something just below this red edge, something in the 600s, and something beyond the red edge in the 700s, that gives you a normalized value for the depth of the absorption of the chlorophyll, which tells you how much chlorophyll you have, which tells you how healthy the plant is. So that's one of the things. There's a bunch of other indices that are associated with water stress and other types of stresses. And then every plant, in addition to protein, it's got a bunch of carotenoids and other pigments, and it's a different ratio in every plant. So in general, each species of plant is going to have a different spectrum. And so speciation is pretty easy using the hyperspectral imagery. Plant stress can be as well. And a lot of people have done some work indicating that when a plant has a particular parasite or infection, its spectrum will change and it can be identified. So there's a lot of work, a lot of the systems that we and our competitors sell are being used for what they call precision agriculture. Yes, sir. I got a whole talk on that. Yeah, there's a pond down in Mashpee on the Cape called Santuit Pond, and it's a shallow pond, and it's surrounded by houses that don't have sewer. They have septic systems, and so there's a constant influx of nitrogen and phosphorus into this lake, and it goes pea green soup in August. And we did a longitudinal study a couple of years ago. We flew the pond in June, we flew the pond in August, and we flew the pond in November, built up a spectral library of the different parts of the different trees, different parts of the pond. And we were actually able, and this goes to this question of speciation, I was able to say, I'm pretty sure that there's two different populations of algae on the opposite sides of the lake. We were working with people who were dragging a Raman spectrometer with a microfluidic system around, and they said, yes, there are two different populations on the different sides of the lake, and they corresponded pretty well with what we saw. I think so. I've not done that. And I told y'all I don't know any optics. I'm a big fan of just doing stuff. I've never been good about reading the literature. And so I know that there are people who are doing this sort of thing. But again, with your satellites, your resolution is kind of low. Yeah. Yeah.
Our partners at RIT, that's something that they've been working on for years.
Not just there. There's a Hobart William Smith College up there in the Finger Lakes region is doing a lot of work on that. It's an important thing. It just, it's one of those things is, can we find them? Yes, we can find them. Can we find them early? I have some evidence from some of the data. When I looked in November after the lake was clear, there was a couple places where my spectroscopy said there was probably algae, these cyanobacteria, and one of them corresponded with a little stream that was draining a fertilized cranberry bog. And so I think we can get some early warning on that. There's more work to be done, and we're an equipment manufacturer. It's hard for us to fund this sort of stuff. So we're still looking for a partner with whom we could work to develop this into, another thing is, in addition to water supply, your state parks department wants to know where to put the fishing bait. And so finding these things. So yes, it's in general, it's hard to see stuff in water, but these highly reflective stuff that are suspended in the water, we can see. Yes.
Question from Sue. What type of noise effects and what type of noise effects have you seen for this type of system in comparison of day and nighttime data?
So, unfortunately, if we're outside, we can't carry our own lights. We got a little drone. In order to get, remember, you got that factor of 100 between the RGB camera and the hyperspectral camera. So you need 100 times as light to get a good picture with the hyperspectral camera than you would with RGB camera. Typically, you need approximately 1 sun illumination. That's a kilowatt per square meter of light to make it all work. We can get that in the lab with a bank of halogen lights. I remember, Jim, you were working on doing littoral surveillance and with a manned helicopter and a big ass generator and banks of LEDs, you can light up the beach, but not with a small UAV. We have enough energy. And so at night, and one of my collaborators from NASA once told me, if you want to take hyperspectral data from the air, the best time to do it is between 10 a.m. and 2 p.m. on June 21st if there's no clouds. And obviously, when we fly at 4 o'clock in the afternoon in the winter, our signal to noise ratio is significantly reduced.
How do you deal with the noise from variations in solar array?
So basically what we do is we have that that calibration panel. We always, you saw that in some of the imagery. We always fly over that, convert everything to radiance. We choose some pixels on that, and we come up with a way to convert radiance pixels to reflectance pixels. And our assumption is that the solar angle doesn't change much in an hour. And so we will recalibrate, we'll refly over that tarp once an hour. There are other ways to do that. There's a technique using the ModTran atmospheric modeling that's built into the ENVI software. It's called Flash. There's another thing called Quack, which is based on this completely impossible, totally a nonsensical idea that if you take 40 independent spectra and average them, it's the same no matter what you're looking at. Seems to be true. And so that you can take these radiance images and you can generate a quick atmospheric correction. It's called Quack using that. So that's another way that's a little more instantaneous. But what we can't deal with is popcorn clouds. If I flew over the tarp when it was bright sun, and then I flew over this patch of ground when there was a cloud, I'm going to get a reflectance value that's 50% of what it's supposed to be. That doesn't reflect the chemistry. That's an error in the data. And so that's why not only does it have to be at noon on June 21st, you can't have any clouds in this stuff. It's okay if there's uniform overcast. You're going to get lower SNR, but you're going to get a more uniform image. Yes, sir.
So you're showing that your system is a ocular spectrometer. And that's quite large volume. And it seems like on a broom, you want to really minimize that. Does that sort of explore other form factors for the spectral splitting?
This is going to be a hard question for me to ask because the guy who designed that spectrometer is standing right in front of me, but it's about this big.
Oh, wow. Okay.
That picture I showed you was one of the larger ones that we use for our machine vision stuff. But the things we're flying, it's about 2 by 2 by 2, so we've miniaturized it in some sense. Yeah. Now that said, we do have other systems that we put up on airplanes and in space that are much bigger. And if you think about spectral resolution, you want a big path length to get high spectral resolution. So we do make some really big systems, but one of the things that our company is concentrated on is making it smaller and smaller and smaller, and having something that flies on this drone that I can carry around with one hand. It's pretty cool, and it's based on having great optical engineers who can design small systems.
And the detector technology is something that in certain cases can really limit us. For CCD and CMOS, it's easier to miniaturize system, but for like that shortwave infrared system, very large Sterling pool camera.
Yeah. In addition to the factor of 10 to 100 in price for using the exotic materials. Yeah. And so Charlie and I did fly our shortwave infrared system on that M300 drone. Worked okay. It's a little bit over the specified takeoff weight, and so we can't actually sell it because nobody's going to be able to get insurance for it. But we're working on, and that's going to be, again, as Dan has just said, if we can find a slightly smaller detector, we might be able to make that work. Yes, sir.
What kind of focal plane do you use for the MWIR?
So we at Headwall have not yet done any MWIR stuff. That was from Bodkin, and I believe those were indium antimonide. And also, have you guys made some with MCT as well for the MWIR? What?
LW.
For the LWIR, but I think we looked at some MCT for the midwave as well. But the INSBE's really good. The mercury cadmium telluride stuff, because it's this alloy and it's a soft material, it's always going to have a lot of defects in it. And so this, the indium antimonide is a much more robust material, getting a lot less defects. They all have to be cooled, but not that cold. Dry ice temperatures is typically what most of these detectors are run at. The long wave ones are going to be more like a liquid nitrogen temperature. I'm here all night, folks. Thank you very much.
This is a piece of trivia. We used to make in 1979. In This was only one microscopy, and the other two actually grew liquid phase.
Oh,
Not in this building, the one across the way. I don't know if that's still exists.
Jim and I used to go look.
Yeah, I worked in this building.
Oh, okay. Yeah, one of our engineers, Bob Long, used to do LPE, MCT as well. I think he was with BDE. No, not BAE. BDE is not. Yeah, that would have been in the 90s, I think.
Zero.
Tell me he used to do LPE. Jim and I met each other when I was he was a postdoc in his lab doing.
I worked in the job after my PhD.
I think that's what he's saying. Stop. Not have our conversation. Goodbye, everybody. I'm leaving now. Thank you all very much for watching.
Good idea.